Hello fellas and welcome to another video of Epoxy channel. In this video we will explore polysulfide epoxy systems, their unique chemistry, key properties and versatile applications across various industries. This is the third video and I hope you enjoy. In addition to curatives, the curing behavior of liquid polysulfide is strongly influenced by certain additives, particularly acid, bases, and moisture content. Reactions involving thiol or RSH groups can be accelerated by the presence of bases and retarded by acids. In practice, amines and related basic components are commonly used as catalysts, while weak acids like stearic or oleic acids serve effectively as retarders. Interestingly, organic monomer captains, though often added as chain stoppers to limit cross-linking, can also act as strong retarders, even at very low concentrations. A notable advantage of activated manganese dioxide or MnO2 is its relative intensity to the exact mixing ratio, offering robustness in formulation and processing. Water plays a crucial catalytic role in the oxidative curing of thiol groups, particularly with activated MnO2. The curing rate increases not only with initial water content but also due to the water release during the reaction, creating a form of autocatalytic behavior. Now, as shown in this table, different curing systems are associated with specific accelerators to tailor the curing speed and mechanical properties to suit various applications. For example, amine accelerators with MnO2 are widely used in construction sealants due to their balanced cure rates and good performance under ambient conditions. Systems based on calcium peroxide or sodium perborate often requires moisture-activated accelerators and are suitable for one-part sealants or moisture-exposed environments. For aircraft sealants, older chromat systems may include specialized organic accelerators for enhanced thermal resistance. On the other hand, removing trace moisture can significantly retard or even prevent curing. Therefore, water scavengers such as zeolites or barium oxides or BaO are often incorporated into the single component moisture activated systems to extend shelf life while maintaining reactivity upon exposure to atmospheric moisture. This table summarizes curative types, their associated accelerators, and common applications areas, providing a clear snapshot of how different curing systems are tuned for performance and processing requirements. Now let's turn our attention to the amount of curative needed to effectively cure liquid polysulfide. The table shown here summarizes the required quantity of each curing agent expressed in grams per 100 grams of the liquid polysulfides. In two-component sealant systems, a small but essential water content, typically between 0.1 to 0.3 weight%, is required in the MnO2-based curative part to successfully initiate the curing reaction. Without this moisture, the oxidative curing process does not proceed effectively. A particularly interesting case is barium oxide or BaO. While barium oxide is commonly used as water scavenger to suppressing the curing storage in one component system, it can also act as catalyst. Once it absorbs moisture, it forms barium hydroxide or BaOH2, creating a basic environment that facilitates the curing. Typically, oxidizing agents used for curing liquid polysulfides are formulated into curing pastes, which include fillers, plasticizers, and curing rate modifiers. These modifiers can either accelerate or retard the reaction. For instance, amine function as accelerators, while fatty acids such as stearic acids or isostearic acids act as retarders. This balance of curating content, moisture presence, and modifier additives is key to tailoring the curing behavior of polysulfide-based systems for different application needs. Now let's talk about the major markets and applications of liquid polysulfides. These materials have carved out a strong position in several demanding industries thanks to their unique chemical resistance, weatherability, and elasticity. Liquid polysulfides are primarily known for their role in the production of high-performance sealants. These sealants are used in a variety of settings, such as in insulating glass units, structural and road construction, and infrastructure projects like water channels, sewage treatment plants, and gasoline stations. They are also employed in more specialized areas like airport runways, concretes and intumescent coatings, freshwater storage applications, boat hulls, decks, and even printing rolls. Their chemical structure allows them to maintain performance under harsh conditions, which makes them exceptionally valuable in these contexts. In aerospace applications, the importance of liquid polysulfides becomes even more evident. Sealants based on these materials are extensively used in the sealing of integral fuel tanks, aircraft fuselage joints, and window systems. They are also formulated into padding compounds for electrical components within aircraft systems. The reason for this preference lies in their outstanding resistance to aggressive substances like corrosion, gasoline, diesel, and jet fuel. These materials also provide excellent adhesion to a wide variety of surfaces, including aircraft-grade aluminum, titanium, and motor protective coatings. What makes them particularly suitable for aerospace use is their ability to perform reliably across a wide temperature range, resisting both cold and heat, while maintaining flexibility and adhesion. Requirements in aerospace are stringent, with demands for fuel and water resistance, mechanical strength, low temperature flexibility down to minus 55 degrees Celsius without crystallization, and heat resistance up to 150 degrees Celsius in intermittent conditions. Polysulfide-based sealants meet these criteria with ease while also offering low permeation rates for fuel vapor, water vapor, and air, alongside a strong resistance to UV degradation. In the construction industry, liquid polysulfide-based sealants are commonly used to bond glass to aluminum frames, fill movement joints in concrete, seal between steel and stone elements, and more. These materials are especially valuable in structures that must withstand long-term water immersion or persistent exposure to high humidity, conditions that typically challenge organic sealant systems. Their chemical resistance and durability makes them ideal for use in water purification systems and wastewater treatment plants, where they must hold up against physical stress, chemical exposure, and microbial attack. Additionally, liquid polysulfides are used in the protection of secondary contaminant areas, zones designed to prevent environmental contamination from spilled or leaking chemicals, fuels, or solvents. They also provide long-lasting sealing and corrosion resistance for bridges and other critical infrastructure. Upon curing, these materials develop a rubber-like consistency with impressive resistance to both water and UV exposure, contributing to their long service life in outdoor and submerged environments. Finally, one of the most significant markets for liquid polysulfide sealants is in insulating glass units, or IGUs. In modern IG systems, the sealant plays a crucial role in maintaining the structural integrity and energy efficiency of multi-panel windows. Typically, a dual seal design is used, where primary seal made of a polyisobutylene provides an effective moisture barrier, while the secondary seal, often a liquid polysulfide-based component, ensures mechanical strength and durability. The secondary seal must be robust enough to keep the glass panes properly spaced and bonded, yet elastic enough to accommodate thermal and mechanical stress over time. What's more, in the event of minor leaks, is the primary seal. The polysulfide-based secondary seal provides a reliable backup, helping to extend the service life of the entire unit. These sealants must also meet a host of performance criteria, including resistance to water and UV light, durability across temperatures from -50 to almost 90 degrees Celsius, and a strong adhesion to both glass and metal. Additionally, they must be easy to apply under industrial manufacturing conditions, and making liquid polysulfides a preferred choice for IG manufacturers. In fact, these materials are so versatile that they can be used both in dual seal systems with PIB as the primary moisture barrier and in single seal IG units when desired. This flexibility, combined with their mechanical and chemical robustness, continues to ensure the widespread adoption of liquid polysulfide across various high-demanding industries. Liquid polysulfide polymers find an important role as flexibilizers within epoxy-based sealants, adhesives, and coatings. By carefully selecting the balancing the type of epoxy resins, the ratio between epoxy and polysulfide, the curing agents, and fillers, formulators can tailor the final properties to suit specific applications. This flexibility in design allows for optimizing depending on the intended use, whether for enhanced flexibility, chemical resistance, or durability. Typically, these systems are formulated as two-component products. One part contains the epoxy resins, while the other combines liquid polysulfide with a curing agent, which is usually amine-based. The separation ensures stability and ease of handling prior to use. Application of liquid polysulfide epoxy blends are diverse and span many industries. They are commonly used in adhesives, protective and barrier coatings, electrical potting compounds, fire protection coatings such as intumescent formulations, resilient tooling materials, as well as epoxy polysulfide mortars and surface sealers. Notably, liquid polysulfides have been promoted as flexibilizer for epoxy resins, with incorporation levels reaching up to 58%. While this level of adhesion enhances flexibility and toughness, it also influences physical strain and reduces the heat deflection temperature as measured by ASTM D648. In particular, the use of low-viscosity liquid polysulfides in the fire-resistant building sealants is an important application. These intumescent polysulfide sealants form a strong carbon-rich foam when exposed to fire, acting as a barrier to heat and preventing the spread of flames. Beyond fire protection, these sealants retain all the desired features of standard polysulfide-based building sealants: excellent flexibility across a wide temperature range, resistance to weathering, chemicals, solvents, and water, strong adhesion to various substrates, ease of application, and non-staining behavior on adjacent surfaces. When designed properly, polysulfide epoxy blends exhibit a range of enhanced properties. They offer improved adhesion to challenging substrates such as aluminum, rusty or oily steel, and even wet concretes. These blends demonstrate enhanced durability, particularly in humid or corrosive environments, along with better chemical resistance against fuel and oil. They also provide improved impact resistance and maintain flexibility down to approximately -30 degrees Celsius depending on the epoxy resin used. In terms of specific uses, These systems excel in applications requiring underwater adhesion, bonding structural elements in wet or harsh conditions such as tunnels, and providing coating that withstand highly corrosive environment found on ships, offshore oil platforms, chemical plants, pipelines, and storage tanks. They are also effective in repairing porous or leaking fuel storage tanks, forming durable, intumescent coatings for steel structures, protecting swimming pools and water parks, and in crack repair for epoxy floor coatings. In adhesives and sealant formulation, the epoxy resins usually remains the dominant component. The liquid polysulfides are added in varying ratio to tune the degree of flexibilization. Adding up to 58% of liquid polysulfide to amine or phenol formaldehyde epoxy resins results in increased flexibility, tensile strength, and impact resistance, while reducing brittleness and increasing elongation. This synergy allows manufacturers to create epoxy system with a balanced combination of toughness and flexibility suited for demanding industrial applications. Liquid polysulfides are highly versatile and can participate in controlled chemical reactions with a variety of other components, including diones, epoxies, triarones, vinyls, and allyl ethers, as well as phenolic resins. These reactions, carefully balanced in stoichiometric ratios, open up numerous commercial opportunities by tailoring material properties to specific applications. A key feature of liquid polysulfide is their thiol end groups, which exhibit strong reactivity toward diisocyanates such as 1,3-toluene diisocyanates or MTDI, diphenyl methane 4,4-diisocyanates or MDI, and multifunctional liquid isocyanates. This reactivity enables the formation of hybrid polymer networks with enhanced performance characteristics. Replacing traditional hydroxy-terminated polymers with liquid polysulfides in these hybrid systems imparts the cured materials with significant advantages. The resulting products benefit from improved chemical and solvent resistance, excellent weatherability, and strong adhesion properties, making them highly durable in demanding environments. Isocyanized cured polysulfide sealant systems in particular offer notable advantages over those cured by oxidative mechanisms. These include superior adhesion to plastic substrates combined with high elongation and tensile strength, which translates to more resilience and long-lasting seals. One of the most commercially important reactions involved the stoichiometric addition of liquid polysulfides to Novolac or bisphenol A or F epoxy resins at ambient temperature. This process forms hybrid materials that combine the desirable traits of both components. The cure rate of these formulations can be significantly accelerated through the use of tertiary amine, such as 1,4-diazoxycyclo-222-octane or DAPCO33LV, or 2,4,6-tris-dimethyl aminomethylphenol or uncommon K54, often with a small amount of ethanol acting as a Lewis base, Lewis acid. This approach yields materials with excellent tensile strength and elongation. At elevated temperature, phenolic resin react with stoichiometrically added liquid polysulfides through a polycondensation reaction, releasing water as a byproduct. The resulting material can be viewed as a block copolymer where the rigid phenolic segments are combined with flexible polysulfide chains. This structure produces adhesives characterized by high flexibility, impact strength, chemical resistance, and strong adhesion to the ware's substrate. Commercial two-component sealants formulations typically include liquid polysulfides blended with pigments, fillers such as silica and calcium carbonates, plasticizers, and various additives like adhesion promoters and antioxidants. The curing agent is prepared as a carefully mixed or milled paste composed of plasticizers, fillers, and catalysts to ensure consistent performance. For one-component polysulfide-based sealants, calcium or barium peroxide is commonly used as the curing agent. These formulations remain stable and uncured in the absence of moisture. When exposed to air, moisture penetrates the system, generating hydrogen peroxide, which ultimately initiates the curing reactions, allowing the sealant to harden in situ. Now this is time to end this session, and I hope you enjoy. Stay tuned for the next slides on this fascinating topic. Thank you.